Alright, so today we are going to talk about the alternating series. Alternating series are series that alternate from positive to negative. They can begin at negative and then go to positive, or they can begin at positive and go to negative. There are two conditions that must be true for the alternating series to converge. The first is the nth term test. So, just like we have done previously, in order for a series to possibly converge, the limit as n goes to infinity of my nth term must go to 0. If it does not go to 0, then the series must diverge. The second is that the terms must be decreasing. So a sub n plus 1, or the magnitude of the terms must be decreasing, must be less than or equal to a sub n. Now, one thing to note, this negative 1 to the n, or negative 1 to the n plus 1, is not part of the nth term. So we are ignoring that at first. Now, what this second step says is that as long as the magnitude of each term is less than or equal to the previous term, and the sequence tends to 0, the series converges. All right, so let's look at an example here. So beginning with, we're going to look at the nth term test. So we want the limit as n goes to infinity of n plus 1 over n. We know that equals 1, which is not equal to 0. So this series fails the alternating series test, and therefore the series n equals 1 to infinity, negative 1 to the n plus 1 diverges by the alternating series test. So now let's look at the second example. Now this one, we don't have a nth term for it, but we can still look and see that the limit as n goes to infinity of a sub n is going to 0. The terms are decreasing. So we passes here. The second, a sub n plus 1 is less than or equal to a sub n. Well, we can see here that 2/3 is not less than or equal to 1/2. It's greater than or equal to 1/2. So it fails the AST here. So therefore, the series, and we don't have a sum series, so therefore the series diverges by the alternating series test. Now, we can use a convergent, for a convergent alternating series, we can use the nth partial sum as an approximator for the value. Now, we know because these terms are decreasing, we know that the error between our estimate and the actual value of the series is less than or equal to the magnitude of the next term, which is the formula that's given here. So let's go ahead and take a look at what that means. We're going to start by proving that this series converges by the alternating series test. So one, we're going to look at the nth term. So we need the limit as n goes to infinity of 1 over n factorial. That equals 0. So it passes there. 2, we have a sub n plus 1 is less than or equal to a sub n. So that means that 1 over n plus 1 and 1 over n factorial, n plus 1 factorial and 1 over n, 1 over n plus 1 factorial must be less than or equal to 1 over n factorial. We know that to be true, so this series will converge by the alternating series test. So now let's take this to the next step, and let's talk about what our sixth term is, or sum of our first 6 terms. So s sub 6 is going to be 1 minus 1/2 plus 1/6 minus 1 over 24 plus 1 over 120 minus 1 over 720. We add this up, we have 91 over 144, which is approximately equal to 0.63194. So this inequality states that s minus 0.63194 is going to be less than or equal to a sub n plus 1. So we need then a sub 7. Well, a sub 7 will be 1 over 5040, which is approximately 0.0002. So now with this inequality, we have that s minus our sum of our first 6 terms is going to be less than or equal to 0.002. Which means if we solve this inequality, we have that 0.63194 minus the 7th term can be less than or equal to our series sum, less than or equal to our 6th partial sum plus our 7th term. So we know that that series is going to be somewhere in between those two values, which gives me that our series is going to be greater than 0.63174 and less than 0.63214. So we'll go over some other examples of that in class tomorrow. So now let's look at some other series here. So occasionally a series will have both positive and negative terms, but it's not going to be an alternating series. For example, let's look at the sine n over n squared. So the sine of 1 we know is going to be positive because that's in the first quadrant. The sine of 2 is in the second quadrant, so that's going to be positive. The sine of 3 is going to be somewhere, so to get to the sine of 3, thinking about the angles, 3 is less than pi, so it's also going to be in the second quadrant, so that's going to be positive. If we continue this, we have the sine of 4 over 16. I know that 4 is more than pi, which puts that in the third quadrant, so that's going to be negative. Keep going, we have the sine of 5. Sine of 5 is not quite to 2 pi, so again, I know over 25. So we're somewhere either in the third or fourth quadrant, but that's negative. And we can keep going, that we know that the sine of 6 over 36, I know that the sine of 6 is going to be in the fourth quadrant because 6 is just less than 2 pi, so that's going to be negative. So this series has both positive and negative terms, but they don't alternate. So the alternating series requires that the terms alternate from positive to negative or from negative to positive. However, we can still determine whether or not this series will converge if we look at the absolute value of each term. So in other words, we're going to look at the sum from n equals 1 to infinity of the absolute value of sine n over n squared. Now, I can compare that to 1 over n squared because the sine of n is not going to be, the absolute value of the sine of n is not going to ever be greater than 1. So I can compare it to 1 over n squared, and therefore I know that that series converges. and it will converge absolutely. Now, that's because if a series defined by the absolute value converges, the original series will converge absolutely. Now, the converse of that statement, if the sum of the absolute value converges, then the series converges, is not true. Okay? If only the absolute value of the terms converge, then we're going to say that it converges conditionally. This is the key takeaway here. A series is going to be absolutely convergent if the sum of the absolute value of the terms converges. It is conditionally convergent if the series converges, but then the absolute value diverges. So let's take a look at a few of these. So we're going to start with, and we always have to check first, the nth term test. So we want the limit as n goes to infinity of n factorial over 2 to the n. That goes to infinity. So AST does not apply. And the series diverges. It fails the nth term test, or it fails the alternating series test, so diverges. Okay, so let's look at this next one. So start with the nth term test. We have the limit as n goes to infinity. The nth term is 1 over the square root of n. That goes to 0. So now we're going to look at a sub n plus 1 is less than or equal to a sub n. So we have 1 over the square root of n plus 1 is less than or equal to 1 over the square root of n. And that's true for n greater than or equal to 1. So both of these are true. But now let's look at the absolute value of these terms. So we have the sum from n equals 1, the absolute value of negative 1 to the n over the square root of n. Well, that simplifies very quickly to 1 over the square root of n, and we know this series is a divergent p-series. So therefore, and normally I write the series down. Actually, let's go ahead and do that. N equals 1, negative 1 to the n over converges conditional. All right, so we're going to do one more example, and then I will let you work through example 4 on your own. All right, so we're going to start with the nth term test. So we have from n equals 1 to infinity, cosine squared n over n squared plus 1. We know that that goes to 0. So next, we need to know whether a sub n plus 1 is less than or equal to a sub n. So this is cosine squared of n plus 1 over n plus 1 squared plus 1 less than or equal to cosine squared of n over n squared plus 1. Well, remember, cosine squared is always going to be between 0 and 1. the denominator is going to grow faster than in the n plus 1 term, than the n squared plus 1. So we know that that's true. So now let's look at the absolute value. I'm sorry, there's just not enough room here to do this well. So we have, and remember, I can get rid of that negative 1 to the n, so we have the absolute value of cosine squared, n over n squared plus 1. Well, this we're going to compare, we can do direct comparison with 1 over that. So we're going to do direct comparison with 1 over n squared, because 1 over n squared will always be greater than cosine squared of over 1 over n squared plus 1. So we can do direct comparison. Therefore, this series over n squared plus 1 converges absolutely. All right, so we're going to stop there. I'd like you to do example 4 on your own, and we'll go over that in class tomorrow.